Hello. In my last class, we discussed the need for snubber circuits, the turn on snubber and turn off snubber. These circuits are required to protect the device against di by dt and the voltage spike across the SCR. How do we limit di by dt? We connected a small inductor in series with the thyristor. Now we know that current through the inductor cannot change instantaneously. And how do we limit the voltage spike across the SCR? We use a RC network. Okay. The second point that we discussed was a high frequency pulse pattern is recommended to trigger the thyristor. Large number of high frequency pulses. How do we transmit these signals from the control circuit to the gate? We used a pulse transformer. See, here is a pulse transformer. Okay. It is a special type of transformer. Why it is special type? The signals or the frequency of the signals that is transmitting from one side to the another side is very high. The principle of operation of this transformer is same as that of a 50 Hz transformer. Okay. Only the type of core is different. See, in a 50 Hz transformer, we use a laminated core. Okay. Whereas a high frequency transformer, ferrite core is used. Ferrite core. Of course, this is a bigger ferrite core, a solid ferrite core. These are suitable for high frequency application. Okay. So there are 4 terminals: primary winding and the secondary winding. Okay. On top it is written 1:1. It implies that the number of turns in the primary winding is same as the number of turns in the secondary winding. Okay. So this is a pulse transformer used to isolate the power circuit from the control circuit. Okay. Now, what are the different types of SCRs? We had different types of diodes. Similarly, there are different types of SCRs also. One of them is, see here, the converter grade SCR. Converter grade SCR. These are slow devices. Okay. They are used in the circuit wherein the frequency could be 50 Hertz. Okay. And the second one is the inverter grade SCR. So these are fast devices, so suitable for high frequency application. Okay. So you see, here is a module has 2 thyristors, inverter grade thyristors. The rating of each thyristor is 45 ampere and voltage rating is 1200 volts. 2 thyristors. See, they are connected in this fashion. See, these are the 2 thyristors. Okay. 3 terminals, 3 power terminals have been brought out. Anode of one, a common point, and the cathode of another. Okay. See, these 2 terminals for supplying the gate signal, cathode and gate, cathode and gate. See here, cathode and gate, cathode and gate. See the contact area, this anode, cathode. So, generally the load current flows through them. So, see the surface area that is available, whereas see the surface area that is available for gate and cathode, a small current is flowing in the gate, okay, and it is mounted on a heat sink. See how elegant it looks. So, that is why I told you in my introductory lecture that the one of the main reasons for the popularity of power electronics is the advances in power semiconductor technology. Okay. So, the rating of this thyristors is given here. I copied from, I downloaded this data sheet from their site. See 46 F stands for fast, 08 ... till 13. This stands for the various voltage ratings. See, if it is only 08, the voltage rating is 800 volts. If it is 13, the voltage rating is 1300 volts. Okay. See, repetitive peak, forward, off state and reverse voltages. Okay. These are the various voltages. Okay. See the RMS current rating, 120 amperes, okay, whereas the average on state current is 45 amperes. Okay. See the surge current rating, 1300 amperes. I had explained to you what is surge current or when it flows, 1300 amperes. And another important parameter, I squared T, current squared time rating, is required to determine the fuse. Okay. 8450 ampere square twice. Okay. See, the critical rate of rise of on state current, di by dt critical, 120 ampere for microsecond. Okay. See the gate trigger current, IGT, 150 milliamperes. Okay. So therefore, just see the gain. Average current rating is 45 amperes. Surge current is how much? Surge current is 1300 amperes. Gate current is 150 milliamperes. Okay. See the gate trigger voltage, 1.4 volts. Okay. Holding current, 250 milliamperes. Latching current, 1000 milliamperes. See, I told you that latching current is higher than the holding current. Okay. So these are the some of the important parameters of the thyristor. Okay. So that's about the conventional thyristor, which conducts when it is forward biased. When it reverse biased, it doesn't conduct. What if input is AC, output is also AC, like fan regulators. See, I have a 50 hertz AC supply, 230 volts, okay, and there is a regulator to regulate the voltage applied to the machine or voltage applied to the fan to vary the speed. Fan is again a single phase AC machine. Okay. So it requires a AC supply. So I have an input AC, output is also AC. So definitely I need to connect two thyristors in anti-parallel. Okay. Now instead of connecting two thyristors separately in anti-parallel, so there is a device available, what is known as a triac. Okay. A triac developed in 1964 by General Electric. Okay. It has a complicated structure, but then functionally it is equivalent to two thyristors connected anti-parallel. Okay. See here is a connection. I have a thyristor 1, thyristor 2, gates are tied together, G, and I am calling this terminal as MT1 and this as MT2. See, I can't call anode and cathode because anode of one is tied to cathode of another thyristor. So there are two equivalent thyristors connected in anti-parallel. So now it is going to be a bidirectional device, remember. It's a bidirectional device. There are two power terminals, but then there is only one gate terminal. So therefore, how do I trigger? A track can be triggered by, see here, making MT2 positive with respect to MT1, okay, and supplying a positive gate current with respect to MT1. Okay. So I will repeat, MT2 should be positive with respect to MT1 and a positive gate current with respect to MT1. It can also be triggered when MT2 is negative with respect to MT1 and by a negative current, negative gate current with respect to MT1. Okay. So here are the characteristics. Two thyristors connected in anti-parallel. Say thyristor 1 and this could be thyristor 2. Okay. These are the VI characteristics. Negative resistance region, unstable. Conduction, forward blocking mode. Forward blocking mode for another thyristor, conduction mode for that same thyristor. Okay. So these are the VI characteristics. These tracks are very popular in fan regulators. See, I showed you a very elegant fan regulator. Okay. Just the knob is brought out. Okay. Everything is mounted inside a switchboard. So there is no power dissipation. That's why it is so small. And I told you this is a power semiconductor device. Has 3 legs. Okay. MT1, MT2 and gate. This is nothing but a track. This is a track. This is a track. So tracks are also used in light intensity controller, okay, temperature controllers. But then what are the limitations of a track? See, I am just showing you the turn-off characteristics of a thyristor. Okay. The current has reversed. It has attained a peak value, the reverse recovery current, okay, and at this point J1 and J2, J1 and J3 have attained the voltage blocking capability. So therefore, a negative voltage is applied across the thyristor, and this happens, this current decays at a very fast rate. Okay. So these are the Turnoff characteristics that we studied for the thyristor. So when this current is becoming 0, the voltage across it is very different from 0. Okay. Now this is for one thyristor, the Turnoff characteristics. When it is turning off, there is a high voltage appearing across the thyristor, the entire combination and across the track. Okay. So there is another thyristor connected in anti-parallel. Now if this dV by dt is high, it may trigger the another thyristor when this current has become 0. Okay. See, this apprehension was not there when in the case of thyristor, because there is only one device, it has to block in the reverse direction as long as voltage across it is less than the reverse breakdown voltage. But then in a track there are two thyristors equivalent, the track is equivalent to two thyristors connected back to back. So when a reverse voltage is being applied to one of them, a forward voltage appears across another thyristor. So that's another thyristor may get triggered because of this dV by dt. Or in other words, track has a less time than the thyristor to recover its blocking power. See, I have written here. It has less time than the thyristor to recover its blocking power. Okay. Or the dV by dt rating is less for the track. Okay. So now let me sum up the thyristor. It is nearly an ideal switch. Why it is an ideal switch? It requires just a sharp pulse to turn on. If 45 ampere thyristor average current rating, maximum gate current is 150 milliamperes. That is required only during the switching or turn on period. When the current is higher than the latching, you can withdraw the gate signal. So the gate power requirement is very small compared to the power rating of the thyristor. Can block both positive as well as negative voltage. The rating of this thyristor is 1200 volts, forward as well as reverse. Okay. Also, high voltage, high current devices are available in the market. The fourth point, device is very rugged, sturdy. But then what is the limitation? It has one limitation. It cannot be turned off by the application of a control signal at the thyristor gate. You cannot turn it off by applying a negative gate current through the gate. Okay. So see here that I have summed all the properties of the thyristor. Okay. So this is the limitation, inability to turn off by application of a control signal at the thyristor gate. To turn off the thyristor, current flowing through it should be reduced to a value which is less than the holding current. Till then it continues to conduct. So how do I make this device which is capable of turning off through gate? Can I do some modifications? Answer is yes. Okay. So there is a device what is known as the gate turn off thyristor, GTO, which is capable of turning on as well as turning off through gate. Okay. By applying a control signal, you can turn off as well as turn on a GTO. Okay. See here, a gate turn off thyristor, GTO. A small power GTO was developed by GE, General Electric, in 1961. Okay. And in 1981, a 2.5 kV 1 kiloampere GTO was developed by Hitachi and Toshiba. Okay. Can be turned on by positive IG and can be turned off by negative IG. And here are the two symbolic representations of the GTO. The same anode cathode structure is the same, a cross here or two arrows, positive IG, negative IG. Okay. So these are the two symbols used to represent a GTO. Okay. What is the structure? In what way it is structurally different from a thyristor? It has 4 layers similar to SCR, P1, N1, P2, N2. Then in what way it is different? How it is being turned off by applying a negative IG to the gate? We will see. See here, P1, N1, P2, N2. One of the difference is thickness of P2 is less in the case of a GTO. Thickness of P2 layer is less. Why? I will tell you sometime later. The second difference is N2 layer is removed by etching in place where gate contacts are situated. I will show you a 3D picture and it will be very clear. See here. See, we have P or P1, N1, P2. See, now N2 is in small places or small islands of N2 are formed. Okay. See, there is one here. See here again, a separate N2 layer, a small island of N2 layer. Okay. So this minus indicates the doping level is very low and the plus indicates doping level is very high. So it's similar to SCR. N2 layer is highly doped, N1 layer is very lightly doped. Okay. So there are large number of small islands of cathode, or in other words, what I can say is that there are large number of GTOs. See here, P1, N1, P2, N2, P1, N1, P2, N2. See here also P1, N1, P2, N2. Okay. And all the cathodes of these GTOs are connected to common heat sink, and that forms a main cathode. So what you can say is a GTO can be seen as a large number of small GTOs in parallel. Okay, as if there is a GTO here, there is another GTO here, another GTO here. One GTO can be seen as a large number of GTOs connected in parallel. Why parallel? Anode is same, cathode is also same. All the cathodes are connected to one heat sink, and that heat sink forms the main cathode. Okay. And another difference between a GTO and a SCR is, in a GTO, gate and cathode structures are highly interdigitized. What do you mean by highly interdigitized? It is something like this. This is interdigitization. Okay. This could be interdigitization. So what is the advantage of doing like interdigitization? The advantage is that now the cathode periphery has increased. Cathode periphery has increased. Also, the distance between a gate and a cathode is very small. If this is gate and this is cathode, this is interdigitization. Cathode periphery has increased. The distance between the cathode and gate has reduced. What is the advantage of this interdigitization? I will tell you sometime later. Okay. Now we just see the structure again. I have a P layer, what is equivalent to P1 in SCR. Junction J1, N layer, lightly doped. Okay. A junction J2 and J3. So when it is reverse biased, J1 should block the voltage, because though J3 is also reverse biased, the reverse blocking voltage of J3 is very small, similar to SCR. Okay. And when it is forward biased, J2 blocks the voltage. Okay. Now there is another structure, we will see here, wherein a N plus layer, in other words a highly doped N layer, penetrates this P1 layer, and it is directly in contact with the N minus layer or the N1 layer. See here in this figure, this N plus layer penetrates at regular intervals, and it is directly in contact with N1 or N minus layer. Okay. So in other words, there is a direct short between the anode and J1 when it is reverse biased. See, when it is reverse biased, entire voltage has to be blocked by J1, because we had a P structure. Now because of this N plus, which is directly in contact with anode and N1, now J1 cannot block the negative voltage, Now the only one junction that can block the negative voltage is J3. Now its reverse voltage blocking capability is very small. So in other words, this structure cannot block negative voltage, or an anode short structure cannot block negative voltage. So this GTO is also known as the asymmetrical GTO. Why? It can block only positive voltage, that is because of junction J2, and it cannot block the negative voltage. If at all if it can block, it is a very small voltage, that is because of J3. Okay. The another advantage of doing this modification is that it speeds up the turnoff process. Now, how it speeds up the turnoff process, I will tell you while doing the turnoff of a GTO. Okay. See, in this a 3D figure I have shown here, same thing, P1 or P plus highly doped, N plus, N minus, P, okay, anode start. Now, coming to the interdigitization, I told you the remote part of a cathode is very near to the gate. In SCR, why did we limit di by dt during turn on? It is because the area that is available for conduction is very small when you turn on the device. It is the area of the cathode adjacent to the gate electrode is available, and afterwards the conduction spreads to other part. Now, what happens in the GTO because of this interdigitization? Even the remote part of the cathode is very near to the gate. Okay. So, in other words, a large area is available during the turn on period, or when at the instant of turn on, a large area is available. So, therefore, you can have a very high di by dt during turn on. Okay. Since the di by dt is very large, so G2O can be brought into conduction at a much faster rate compared to SCR. This is because of interdigitization. Even the remote part of the cathode is very near to the gate. So, large area is available, you can have a very high di by dt. So, if I can have a very high di by dt, I can, or turn on time of the GTO reduces. Okay. See, in a 3D it looks something like this. I have chosen a anode short structure. Okay. So, these are the gates and the cathode, the direction of holes, the direction of electron. Okay. So, GTO can be brought into conduction very rapidly, that is because of a very high di by dt is possible. Okay. Now, coming to the turn on characteristics, they are similar to an SCR. There is no much difference between the SCR characteristics and the GTO characteristics. It is a latching device, in the sense, in principle, gate signal can be withdrawn once the anode current is higher than the latching current. Okay. But it is recommended that a positive Ig is maintained throughout during the conduction period. Why? It is because of this reason. I told you one of the limitations, or one of the difference between a GTO and a SCR is that holding current for a GTO is much higher compared to an SCR. Holding current of a GTO is higher compared to a SCR. Now, assume that during some disturbance, anode current has dipped momentarily. Okay. Since the anode current has dipped momentarily, some parts of the GTO might turn off. Okay. And now again the anode current increases very rapidly. The area that is available for conduction is very small. Okay. So, therefore, there could be some hot spots, and because of this localized heating, a GTO may get damaged. Okay. So, therefore, it is recommended that during conduction period, a positive Ig is maintained throughout. Okay. but then you don't need to maintain the same magnitude of the gate current. Okay. So what is being done is a high pulse of gate current is provided during turn on, so that the turn on time can be reduced, and after some time you can reduce this gate current. Okay. See, the waveform looks something like this. Okay. A high gate current. So anode current has attained a steady value. After some time, TD, what is known as the delay time, the cathode voltage, the voltage across the device also has reduced to its saturation value. So after some time you can reduce the gate current to IGT. So this value is approximately 10% of this peak value. Okay. G. Okay. So that is about the turn on of the GTO. Now coming to the turn off of a GTO. So when, even in the case of a thyristor, when the thyristor is on, both T1 and T2 are in saturation. That's why the voltage drops to a very low value. Okay. Could be of the order of 1.5 volts or so. So T1 and T2 are in saturation. Now you want to turn off the GTO. Okay. So first thing that has to be done is you have to bring the T2 out of saturation. Okay. See in this figure. This is a T1, a PNP transistor, and this is a T2, a NPN transistor. Both are in saturation. Okay. Now device has to be turned off. How do I turn it off? We have to bring this transistor out of saturation. How do I bring this transistor out of saturation? I have to reduce the base current. Okay. Now let us see what is the relationship between the anode current and the gate current that is flowing out of the gate terminal. Okay. See, this expression that we have derived for the SCR is still valid here. The total saturation current is given by alpha 2 into Ig plus ICBO is the sum of ICO1 and ICO2 divided by 1 minus alpha 1 plus alpha 2, okay, wherein alpha 1 and alpha 2 are common base current gains. We have already defined them for the SCR. When SCR is in on state, we have reduced the gate current to a very small value. Okay. So in on state, I can neglect this term. So IA can be given by ICBO divided by 1 minus alpha 1 plus alpha 2. See here. Is the current that has to be turned off. See, in the previous equation, IA becomes 0 when the numerator becomes 0. So when can you make this numerator 0? When ICBO is equal to minus of alpha 2 plus into Ig. See here. So the relationship is Ig is equal to minus of ICBO divided by alpha 2. Okay. So if I want to find out the gain or the relationship between the anode current and the gate, it comes something like this. Okay. IA divided by Ig is equal to alpha 2 divided by alpha 1 plus alpha 2 minus 1. Okay. How do I improve this gain? In other words, how do I make this gain as high as possible? Alpha 2 should be as high as possible. What is alpha 2? It is the gain of N1, P2, N2 transistor. See here, alpha 2 for this transistor. This is N1, P2, N2. How do I make alpha 2 as high as possible? One way is to make the thickness of P2 layer less. Okay? P2 layer should be very thin. See, that is one of the difference between an SCR and a GTO. I told you the first difference that I told you is layer of P2 is less compared to an SCR. And second is increase the doping level in N2, thereby increasing the value of alpha 2. Okay. Now, how to turn off a GTO, or what happens exactly during the turn off process? Ig has reversed. Ig is flowing out of the gate. Ig is connected to P2. Okay, see here. Ig is the P2. Now Ig is flowing out of the gate terminal. So holes are extracted from P2. Okay. So as this extraction takes place, the voltage drop is developed in the P2 region. I'll tell you, holes from the anode are extracted from the P base. Okay. So during this process, a voltage drop is applied in P2 base region, and eventually this voltage reverse biases your gate and cathode junction and goes into cutoff. But then entire turnoff process isn't completed as yet. As the hose extraction continues, P2 is further depleted. Okay. See, first is gate cathode junctions gets reverse biased, okay, but then Ig is still flowing out, so P2 gets further depleted. What happens? Conduction area drops. Now the current may be flowing in the remote parts of the anode, okay, or far away from the gate. Now it may so happen that the current density in those parts may increase, and if this happens, there would be a localized heating and device may fail. Okay. So this has to be avoided. This has to be avoided. Okay. See, the figure that's showing the turnoff process is something like this. All the holes are diverted towards the gate. It is being okay. The P2 gets further depleted. Now anode current tries to flow through the area which is far away from the gate. Okay. Area, there is a reduction in the area that is available. Now it may form, or in that area the current density may increase, localized heating, eventually device may fail, okay, during the turn. Now the turnoff of a GTO is greatly influenced by the turnoff circuit. Unfortunately, turn-off gain of a GTO is very low. Turn-off gain is very low. Could be of the order of say 6 to 15, okay, generally. So therefore, if anode current is 100 amperes, by the way, GTO is a high current, high voltage device. Okay. So if anode current is around 100 amperes, gain is of the order of say 6 to 15. So gate current that is flowing out of the terminal is 10 amperes, and is fortunately for a very short duration. Okay. So as the gate current starts flowing out of the terminal, for some time anode current remains constant. Okay. So this period is known as the storage time. See in this figure. At steady state, gate current we had reduced the gate current to a very low value. Somewhere at this point, you decide to turn off the GTO. So IG reverses. Okay. Though IG has reversed, IA still remains constant for Ts duration. Okay. So this is known as the storage time. Okay. So during storage time, anode current remains approximately constant, and this period Ts can last for few microseconds. Now what happens after Ts? Okay. Now this process has to be studied by taking a snubber into account. Okay. There has to be a snubber circuit to turn off a GTO. Okay. I told you di by dt rating of a GTO is very high. So you can use a very small inductor in series with the GTO. Okay. We had connected an inductor in series with a thyristor to limit di by dt during turn on. Similarly, to limit di by dt, you require a very small inductor, since the rating of di by dt even for GTO is very high. Okay. Now there has to be a turn off snubber, a RC circuit, say looks like this, something like this. Okay. Now there is a diode, it has its own turn on time, and I have shown a small inductor, what is known as a loop inductance, in dotted lines. Okay. A very small inductor in dotted lines. You wanted to turn off the thyristor, so Ig has reversed, for some time Ia remain constant, and from Ts onwards anode current falls at a very fast rate. Okay. Now because of this loop inductance and because of this diode, turn on time of the diode, this current, anode current, cannot start flowing through the snubber circuit immediately. Okay. And because of this, there is going to be a voltage spike. Okay. Because of the inductance which is there in other parts of the circuit. If this inductance 0 and turn on time is very small, then maybe immediately this anode current finds a path to the capacitor. Okay. Now because of this inductor and diode, okay, this current gets choked, and therefore because of this a large di by dt, a spike appears across the GTO. it could be dangerous. In the sense, device may fail because of this spike. Okay. So therefore, the snubber circuit layout is very important. The loop inductance, the inductance that I have shown in dotted lines, should be as small as possible. Snubber circuit layout is very critical in the case of a GTO. Okay. So the anode current has fallen to a very low value, so at the end of TF period. It is known as the fall time, and this is very small. Okay. And from there onwards, a current, what is known as the tail current, starts flowing through the snubber circuit. Okay. Now, the voltage across the GTO is limited by the dV by dt, is determined by the dV by dt. Now, what is this tail current? This tail current, at that period IK is equal to 0, cathode current is 0, okay, and the gate current is same as the anode current. Okay. So this tail current is corresponding to the free charges they exist in N1 layer. N1 layer. The current due to the free charges which exist in N1, which is nothing but the blocking layer, lightly doped layer. Okay. These carriers are numerous and they require a finite time to recombine. See, the problem here is, as the voltage rating increases, N1 layer, the thickness of the N1 layer increases. As the thickness of N1 layer increases, okay, time taken for these carriers to recombine also increases. So in other words, the tail current period increases with the blocking voltage capability of the GTO. Is that okay? So what is the consequence of having a higher fall time, or sorry, higher tail time? See, voltage across the device has started increasing. Okay. Current in the device is still finite, the tail current. Voltage is a reasonably high value it has attained. So therefore, the losses that are taking place device are high. So turnoff losses in a GTO, they are significant. Okay. So how do I reduce the turnoff losses? So one way to reduce is to reduce the fall or tail current duration. How to reduce the tail current duration? This TT has to be reduced. Having decided on the voltage rating, N1 layer, thickness of N1 layer gets decided. Okay. And the tail current depends on the thickness of N1. Is there a way out? Yes. Why did we do anode shorting? I said one of the advantages of anode shorting is to reduce the turnoff time. How does it do? What it does is, see this, those anode shorting N layers are highly doped. They were all were N plus. They are highly doped. So what they do is, this heavily doped N cells, they make the minority carriers trapped in N1 recombine more quickly. Okay. So this highly doped N cells, they helped the minority carriers trapped in N1 recombine more quickly. So therefore, your tail current time reduces. Is the tail current time reduces. But then device is no longer symmetrical. Now it can block only the positive voltage, negative voltage it cannot block. Okay. So with this I will conclude my today's lecture. Thank you.